Hello. Can you hear me? So, can I share my screen now? Can you see my screen now? Okay. So the video and the sound is clear. Okay. Hello everyone. This is Mustafa Al-Jumaidi from the University of Tennessee, Knoxville, in the United States. And today I will talk about our work, that is the combined beamforming and waveform design using the mid-band frequencies for 5G and beyond networks. This work has been done with the cooperation of the authors listed in this paper or this presentation. First, I will talk about the motivation for this work. Then I will talk about why we need hybrid beamforming and why we don't use the cyclic prefix OFDM based waveforms, and we use other types of waveforms. Then I will talk about the assumptions and the system model for the beamforming and waveforms. Then we will talk about some numerical and simulation results and conclusions and future works. First of all, the mid-band frequencies, or the C-band, or the 3.5 gigahertz frequencies that we mean in our work, and the millimeter wave frequencies in the 24 gigahertz and beyond or above are now essential parts of the 5G and beyond networks. These high frequencies provide a huge amount of bandwidth that is underutilized so far, but they have some drawbacks or limitations because they are suffering from higher path loss and higher effect from the rain and atmospheric absorption, blockage, mobility, and all the other effects, which means that we need the beamforming to send narrow beams instead of the omnidirectional transmission in all directions to make these frequencies go further distances. Also, the OFDM, orthogonal frequency division multiplexing waveforms have been used for many years now, and they are great with a lot of benefits, but at the same time they are also having some limitations that we are trying to avoid in our research. So now we are trying to combine the effect of beamforming and non-orthogonal, non-OFDM waveforms together and see their effect on the overall performance. So first of all, why we use the hybrid beamforming? There are many reasons to select the hybrid beamforming. There is basically the analog beamforming, where we have only one RF chain, even if we have large number of antennas, which give us only a limited amount of spectral efficiency or utilization of the spectrum. On the other side, we have the digital beamforming, where we have as many RF chains as the number of antennas, but it is difficult to build, and it is not efficient from hardware point of view, and it consumes a lot of power, emits a lot of heat, and it is not feasible from like a commercial point of view. So the hybrid beamforming is considered as a combination or hybrid of the advantages of both types, and avoiding the disadvantages of each of them. So here we can see that in the analog beamforming we just use phase shifters in the analog part. In the digital beamforming we do everything in the digital baseband. For the hybrid beamforming we are just analyzing or performing the beamforming into two parts. Part of it in the digital side and part of it is in the analog side. That's why we call it hybrid beamforming. On the other side, and as part of our work, why we need new waveforms. Orthogonal frequency division multiplexing have been used for many years, and it is really simple to build, and it is compatible with fast Fourier transform, but as we said, it has some of drawbacks or limitations because it needs a lot of synchronization. It suffers from a high peak to average power ratio, and it is sensitive to carrier frequency offset. It is sensitive to Doppler shifts, and it requires linear transmission circuitry, which reduces the power efficiency, and it suffers from the loss of efficiency, which is caused by the cyclic prefix, and as we said, it has a lot of out-of-band emissions. So a lot of new waveforms have been suggested to reduce or fix some of these limitations. For the beamforming, as we said, we are trying to build hybrid beamforming, and a lot of designs have already been suggested, like hundreds or even thousands of designs. In our design, we are just trying to use a simple method of matrix factorization, by obtaining the fully digital beamforming matrix from the channel matrix, and then we just try to apply something called LU decomposition by just factorizing this matrix into two matrices that their product gives us the fully digital beamforming matrix. By doing so, we have been we reduced the complexity from big O of n cubic to big O of 2/3 of n cubic, and we got faster system and less hardware complexity or structure. And at the same time, we are achieving almost the same spectral efficiency that is achieved by the fully digital beamforming. This system has been suggested and published in the VTC 2019 last year. Basically we are depending on this kind of methodology, where first of all the base station will send some preamble or pilot signals. The user equipments will send the feedback. By this time the channel matrix H will be well known for the user equipment and the base station. After constructing H, we apply the singular value decomposition to get the fully digital beamforming matrix. After that, we perform the LU decomposition in the transmitter side and the receiver side. Then we construct our beams, or the hybrid using the hybrid beamforming and the matrices that we got from the LU decomposition. And then the directional transmission between the transmitter and receiver through narrow beams will start. And we are trying to make sure that the beams of the transmitter and the beams of the receiver are aligned towards each other all the time. On the other side, as we said, the cyclic prefix OFDM that has been suggested for the 5G and before that in the 4G and a lot of other types of networks suffers from a lot of limitations. So now in the UFMC, or the Unified Filter Multi-Carrier, we are suggesting some kind of a new design, which is shown in this figure, where it has a lot of advantages over the OFDM, where we for each resource block there has its own filter or TX filter, and we have some kind of zero guard bands between each successive inverse fast Fourier transform. And all of these will reduce the out of band emission and also reduce the intersample interference. By using or combining the hybrid beamforming using the LU decomposition and the universal filter multi-carrier waveform, we tried to build some kind of this system where we compare the performance of the system when we use cyclic prefix OFDM and the performance when we use the UFMC. This is some kind of diagram to show the experiment, where first we set the parameters for the system, for the simulation system. Then we set the parameters for the 5G environments. We use two types of channel models, the additive white Gaussian noise and the extended Pedestrian A model, with different features and parameters. Then we use the combined beamforming and waveform by using the two types of waveforms and compare their performance, and we use the hybrid beamforming design that we talked about. Then we do the simulation and using the MATLAB and LabVIEW, and then we calculate some numerical results to show us the benefits of using the UFMC over the cyclic prefix OFDM and the benefit of using beamforming for MIMO systems. This table shows us some of the simulation parameters that we used in our system, and as we can see, we use the frequency band 3.6 GHz, the bandwidth is 10 MHz, and resource blocks is 50, and the others as shown here. And of course there are more details in the paper. First of all, we tried to compare between the 1x1, which is SISO, single input single output antenna, using the OFDM, and we see the throughput of the system using the additive white Gaussian noise channel model, and comparing that with the other MIMO systems, 4x2, 8x2, 2x2, and 6x2. And we can see that the more MIMO we have, for example here in the 8x2, using the UFMC, we will have like better and superior throughput compared with the smaller MIMO structures, and this is thanks to the UFMC and the beamforming combined. Then when we change the channel model to the EPA, and there was we expected to have like a degradation in the achievable throughput, but we saw that the throughput remained the same and even got better in some situation. Again, thanks to the UFMC and the beamforming. So here we can see that for the 1x1 SISO, it achieves specific type of throughput, and the more or the bigger MIMO system with beamforming and waveform, that is UFMC, we can achieve better throughput, even for mobile users in the pedestrian, extended pedestrian I model. These are also some additional results that, and of course there are some details about that in the paper, if someone is looking for more details. Finally, for conclusions and future work, we saw that here we tested the effectiveness of using both of the beamforming and different waveforms, and we saw that the new waveforms, that is non-OFDM, can achieve better performance when combined with beamforming or the right design of beamforming. Different combinations of MIMO, beamforming, and waveforms have been tested for realistic environments, realistic channel models. This work also can be extended further for higher frequencies in the millimeter wave band from 24, 28, 39, and even higher frequencies that are now part of the 5G and will be even part of the 6G and beyond. Also, the effect of serving more than one user at the same time, or the multi-user massive MIMO, is also a good direction for future investigation, and this is some of the work that we are working on right now. Also, finally, thank you for listening, and if there is any question, I will be happy to answer them.
Thanks for your presentation. Dear participants, do you have any question about the article? Okay, no question. I wish you continued success in your career.
Thank you so much.
Mustafa.
Thank you.